about chapter 2 or proofs in this lecture. So you're going to go through different sections within your Zybooks, and we're going to cover this in parts. So the first part being your proofs. When we talk about proofs, you have multiple different ideas. So there are words you need to understand. So theorems, proofs, and rules of inference being some of them. So a theorem is essentially a statement that can be shown to be true. Axioms or postulates are statements that you've been given and they're assumed to be true. Proof is essentially what we do in our day-to-day life. It's a sequence of statements or a valid argument that you know can prove that theorem true. And then rules of inference, basically these are rules used in different proofs to draw conclusions based on assertions that are known to be true. Now you also have pre-theorems, corollaries, which is a post-theorem, and then a conjecture, which is essentially a statement which is assumed to be true or believed to be true, but there's no proof for that yet. That idea still remains the same here. We're not actually going to go into this for a little bit. This is just a reminder for all types of valid arguments. So recall that an argument is a sequence of different propositions. The final proposition is called the conclusion, and everything else along those lines or all the previous propositions are called premises or hypothesis of that argument. Now, an argument is valid only if or whenever the truth of all of its premises is true, and it's true to the conclusion itself. So how do you show that Q logically follows from the hypothesis that's given? So essentially you have to show that the whole P1 and P2 and such going into makes Q a tautology. Essentially that's how you're going to go with that. So one can use different rules of inference to show the validity of an argument. You also have something called a Walker's proof. Now this is if one of the premises is false, then that entire argument that you've been given, it can be Walkersly true, since false implies anything. Basically, let's not get confused with this for now. For now, we'll go into what matters. So you have different theorems that involve different statements for universally quantified variables. So if x is greater than y, where x and y are both positive numbers, then x squared is greater than y squared. We've done this, we've established this quite infinitely. So quite often when it's clear, theorems can be proved without explicitly actually using different laws. You can just use generalization, and you can use instantiation to actually go about with it. There are different methods of proof, and we're not actually going to go into all of these. We're just going to focus on direct proof, proof by contradiction. We'll go into proof by cases and such as well. So the first one that I actually want to discuss is proof by exhaustion. It is what the name suggests. The way you actually define all of these, it's easier to apply language logic. That way you kind of remember and understand how it flows. So essentially for your proof by exhaustion, you've been given a domain for that specific universal statement which is small. Then you can basically prove the statement by checking all the individual elements. This is proof of exhaustion. You can disprove this by essentially creating a counterexample, which is something that shows that that universal statement is false. So to give you an example, if we check for every integer n such that 0 is less than or equal to n is less than 3, that statement exists. Now the domain is quite small. Essentially you have 0, n can be either 0, 1 or 2. So just apply all three into this specific logic and see if it applies. So when n is equal to 0, n plus 12 is equal to 1 and n3 is equal to 0. So 1 is greater than 0. Same when n is equal to 1, n plus 12 is equal to 4 and n3 is equal to 1. So that kind of helps understand. Again, you get something which is 4 is greater than 1. So this kind of helps understand that, okay, the first two statements are true for sure. Now you have n equal to 2, n plus 12 equal to 9. So n3 becomes 8, 9 is greater than 8. So it kind of satisfies all our requirements, and we've proved by exhaustion by using all the three integers that existed within that domain to prove that our theorem is true. Now, along the same lines, if you wanted to disprove this, if I said something along the lines of every month of the year has 30 to 31 days, this is false, or this can be disproved by essentially saying February only has 28 days and on occasion 29 days. So that's the disproof by exhaustion also, or that's essentially your disproof for this specific case scenario. Now the next method is direct proof, and this is going to get used quite a bit. So in this case scenario, what you do is you assume P, and from P you derive Q. So you just want to work off of that idea. So within direct proof, you have a conditional statement. The hypothesis P is assumed to be true, and the conclusion is proven as a direct result of the assumption. So to prove a universal statement such as is given, within step 1, you essentially, for the arbitrarily chosen element of the domain, whatever the domain may be, like C, you assume a specific hypothesis for that pattern. So for P of that conclusion, you assume that it's true. Then for step 2, using the previously established results and definitions, prove that the conclusion, which is Q of C, is also true for C. And then because P of C is true and Q of C is true, conclude that this statement is true. It becomes a universal generalization. In this case scenario, a rational number is defined to be a number that can be expressed as a ratio of two integers in which the denominator is non-zero. This is your basic math. Nothing else has changed here. I'm just defining it. So it helps correlate different numbers as we go through them, or different ideas. So let's go into an example of direct proof. So the theorem is that Mary is a math major or a CS major. If Mary doesn't like discrete math, she's not a CS major. If Mary likes discrete math, she is smart. And Mary is not a math major. So there are 4 statements here. And now we need to conclude whether Mary is smart or not. So if you start thinking, what's the chain of reasoning here? You can create certain assumptions, right? So we can think of Mary is a math major. Based on the first statement, Mary can be a CS major, or Mary is a CS major. Mary likes discrete math, and Mary is smart. This is based on the different statements that they've given us. Once we have that, we can essentially create our statements. We can create our conditional statements, which you know how to create, and these are essentially what these imply. Once we've created those, we can now write our proof statement, where you're defining what the different statements are. You're combining them together to see if the Mary is smart conclusion can be proven true. So in general, to prove P if Q, assume P and show that Q follows. That's essentially again what we've done. We've taken all the statements, we've combined them together, and then we're trying to prove whether Mary is actually smart. So this is essentially what we have. So you have different given statements, the 4 statements that are given, and based off of that, now you're going to draw different conclusions, which if we look at this, Mary is smart, because we ran through the different scenarios. If you look at this, all the statements are actually apply, and then Mary is smart, QED, because she actually does have a QED, and then I rest my case. This is essentially how you're demonstrating what happened there. Again, take all the statements, combine them together, define whether it can actually work or it cannot work. And these are, again, look at these, make sure you understand how you play with these, because statements, when you actually start writing proofs, you're going to have to go through different statements and write them down. That way it makes sense. Another example is if n is odd integer, then n square is odd. Now, let's define this before we actually go into proving something. So the definition being integer is even if there exists an integer k such that n equal to 2k, and n is odd if there exists an integer k such that n equal to 2k plus 1. An integer is even or odd, and no integer is both even and odd. Again, this is your basic math. We're just defining it. That way we can actually play with different ideas. So now the theorem is, when you have a domain of a given given P, then Q needs to apply. So where P of n is an odd integer and Q of n is n square is odd. That's based on what the statement is given. And now we need to show that if P, then Q. So if n is odd integer, then n square is odd. So let's prove this. P is an odd integer, Q is P, or P n is an odd integer, Q n square is odd. We want to show that P is Q, or P if Q. So assume that P n is odd. By definition, again, this is some integer, and therefore you need to make sure that you can actually square out the whole equation, which by definition is again an odd integer or an odd number, which we can see right here. So again, go back to different definitions, start by creating direct proofs. The next idea is proof by contradiction. This is also called as indirect proof. A proof by contradiction starts by assuming that a theorem is false, and then it shows some logical inconsistency, and because of this assumption. So based on this, essentially it's exactly like when you go around talking to your friends. Somebody says something and you're just assuming it's false, and then you're going to work off of that based on some logical inconsistency. So the idea is, in order to prove that P if Q is a tautology, we prove that P, when essentially you make sure that the contradiction is actually existent, and then you have negations of each other. I'm actually not going to say that out loud because it's just going to create a lot of confusion. Just read through it, that way I don't confuse it. But if we assume that the theorem is false, where your negative P is negative Q, where negative Q exists, then the assumptions P is true, then we need to reach a contradiction that whole statement, the inconsistency or the contradiction, basically is false. So let's say we want to prove P. So we show that negative of P is false. Essentially, it's a false statement. So once we conclude that P is false, since 1 is true, therefore P is true. If the negative of something is false, essentially the positive becomes true, just to make it easier. Now we want to show that P if Q, assume that the negation of the conclusion, that is negative Q, you assume that negation, then you show that P and negation of Q is false, and since that is false, then basically we don't need to prove it. We can essentially say we are done. Let's go through an example. This may make it easy. So you have 3 different statements here. Rainy days make gardens grow. Gardens don't grow if it's not hot, and when it's cold outside, it rains. Prove that it's hot. So now how do we begin this? So let's assume, we can make an assumption that if it's not hot, then it's cold, or if it's cold, then it's not hot, right? So let's do that. So you have 3 different statements now. R is rainy day, you have 3 different variables that you're going to start using. R is rainy day, G is garden grows, H is it's hot. Now we start working off of that. Given that R if G, essentially rainy days make gardens grow. Second statement is gardens don't grow if it's not hot. And then third statement, if it's hot or when it's cold outside, it rains. So now we need to show H, which we can do by adding all of those or creating a AND statement together for all of them and then proving that it is hot. The conclusion needs to be that it is hot. So let's go back again to what the statements are. You've been given those 3 statements. We need to show that it is hot. Based on that, we assume a 4th statement, which is assume to the contrary. We're going to assume it's not hot. Once we know that, now we can start working on different assumptions. So R, now based on the 3rd and the 4th statement, exists. G exists, and not G exists based on different statements. We also have a 4th one, which is essentially a contradiction. Once you have a contradiction done, once you know that all of this exists, Essentially, it is hot. So we basically assume whether it's hot or it's not hot. You can define this. I mentioned this earlier. So you can either define it's cold. You can go with cold also. It depends on how you decide to play with it. It's called the law of excluded middle. In certain complex arguments, this is essentially not very valid, and you're going to have to work with this. So I don't necessarily use it all the time, but there is something called constructive mathematics because of which it actually came about, and that's where we're working with this. Give you another example, classic proof that square root of 2 is irrational. So first, you suppose that square root of 2 is rational. That's essentially the contradiction that I've been talking about. You just assume that it is different. And then square root of 2 is equal to a divided by b for some integers, and where a and b relatively prime, no factor in common. This is actually very intelligent because you can work off of different statements here. Now, square root of 2 equal to a by b implies that 2 is equal to a square by b square. This is normal. We've just taken the square root and moved it around. Once we've done that, we can move things around where 2b square equal to a square. And now if a square is even, so a is even as well. For some specific case, this could obviously be different. Now 2b square will also have to be even in that case scenario where 2k square equal to 4k square. So b square is equal to 2k square. B square is even, so b is even. B is equal to 2k for some k. But if a and b are both essentially even, then they're both not relatively prime. So again, here we first went with the definition of different concepts. Now once we know what a rational number is, it kind of makes sense. Definitions help provide different premises, and then math is again what definitions has. So it's essentially just that. Now I know you're not going to let me get away with that, so let's go with that. A square is even, so a is even. A equal to 2k for some k. Suppose let's go with the contradiction where a is not even, because I said it's not even, right, at some point. So let's say it's not even. Then a becomes 2k plus 1 for some integer k. Remember, we went through this definition earlier. If this is true, then now create a square for both of them, where you get 4k square plus 4k plus 1. And a square is odd, because we decided that it's not even, right? So now this is a contradiction. So a is actually really even. We weren't bluffing there. A has to be even in this case scenario. And this is essentially what you do for proof by contradiction. That's it for now. Thank you.